Hi, so in this video, we're going to take a look at matrices. And here's where, from the point of view of writing this book and teaching this course, you have to make a decision. Because there's actually two libraries that are really appropriate for studying matrices. The first is SymPy, and the other one is a library called NumPy. And there's chapters about NumPy later on in the book. NumPy is an incredibly important library for doing mathematics with Python. But we are going to stick with SymPy. And the reason for that is SymPy allows us to handle matrices that have symbolic variables in them. NumPy, N-U-M-P-Y, is, again, mainly numeric. So for that, it's all about having numbers and doing that efficiently. So we're sticking with SymPy to handle matrices. And we're going to see how to calculate the determinant and how to calculate the inverse. So here we go. Okay, so we get in this matrix, and we're asked to find its determinant. That'll obviously be a function of this symbol A. And then we want to find the values of A for which A is singular. So that's when the determinant is equal to 0. Following on from that, we want to calculate A inverse and verify it by computing A times A inverse. So let's go ahead and get started with that. I'm going to create a new notebook, and I will call it, similar to the name of the chapter, matrices. And we start off by importing SymPy as sim. And now I create our variables. So the first thing is to create this symbol A. And then we're going to start creating our matrix. And just to illustrate a few things, when we're dealing with a matrix, we've got all these entries in this array, this square. But another way of thinking about that is that a matrix is a collection of rows. Row 1, row 2, row 3, etc. Okay? And that's indeed how we pass a matrix, how we create a matrix in Python. And the way we do it is we use these square brackets. So we put our row entries in a square bracket, and then our other square bracket with our row entries in it, and so on and so on. And we put all our rows in square brackets inside one big square bracket. So that's what we're going to do here. And so we create the matrix A to be the matrix. And we open one square bracket for our rows, and then it's, now I'm just writing this down. So the first row is A11. So it's A, and then we use commas to separate the entries, 1, 1. Then the next row was 1A1, and then the next row was 1, 1, 2. Oops. And we can take a look at A, and we have that. So the first thing we can do is calculate the determinant of A, and we do that by calling something that's called a method, and we'll see that later. But it's essentially a tool that every matrix in SymPy has on top of it, and we access it by using dot and then det for determinant. Open and close the brackets. And we do that, and it's calculated our determinant for us. We're going to use this, so we're going to say determinant is equal, and we'll take another look at our determinant, and we see that we have that. So a matrix is singular when it has determinant 0. So we do solve set determinant, and we want to solve for A, and we indeed get that when A is 0, obviously this term is 0, and when A is 1, again, this term is 0. So going back to the question, we see for the following values of A, find A inverse. And so immediately for the first two, we can't. But we can check, we can just confirm that. So if I do A dot subs little a equals 0, that's my matrix. And the way we get the inverse is on that matrix, in the same way that we did with determinant, we do dot, and then inv for inverse, and open and close the brackets. Very important to not forget to open and close the brackets. And it comes up with non-invertible matrix error. So you can actually see some of this. This is called a traceback. But essentially, this is some of the code that was happening in the background that it was trying to do. And it eventually collapsed and said, I can't invert this matrix. Matrix determinant equals 0, not invertible. So if you think about this, this is kind of showing all the workings where you would have by hand tried to invert it and eventually come to the conclusion that you can't. So we won't do that. Indeed, if we do it for 1, we get the same thing. But if you substitute 2 in there, we get the matrix, its inverse is given by that. And the question asks then to confirm the result by computing A times A inverse. And so the way we're going to do it is we're going to take our matrix A and we want to multiply it by this, right? So our first term is there and our second term is there. And the symbol for matrix multiplication is the at symbol. So if we do that, we do indeed get the identity matrix. And indeed for A equals 3, we again get the identity matrix, which is that part of the question, okay? If you look at the how-to section, what we've done there is create a matrix, calculate the determinant, calculate the inverse. We haven't multiplied it by a scalar, but you can take a look at how to do that. Add matrices together again. We haven't done that in the tutorial, but please do take a look. Multiply matrices together. That's that final thing we did, which is that ampersand. And then finally, how to create a vector. A vector is really just a matrix with either one row or rows with only one entry in it. So we've kind of seen how to create a vector, and then how to solve a linear system that is defined by a matrix and a vector. That's in there as well. So do take a look at that. And then again, you've got the exercises and the solutions, and then there's a lot of further information as well. So there you go. Once you've worked through that, you've got the tools available to you to use a computer to work with matrices.